Okay, so we're gonna talk a little bit, switch a little bit of gears, I guess, transition a little bit into, trying to understand why it is that reactions come to equilibrium. And in order to understand that, we really have to talk uh, a little bit about thermodynamics and the energy of the system to be able to understand why equilibrium occurs as opposed to everything just going directly to completion like we'd expect in a stoichiometric reaction. And so, the whole idea of chemical reaction is that chemical reaction occurs because of the energetics of the products and the reactants. And everything sort of revolves around that. Now, there's a little bit of a caveat in that there's another governing factor called kinetics, or the rate of the chemical reaction, that's going to be important for us to understand. But we're not quite there yet, and that's what we're going to come to next. We're going to talk first, though, about the energetics and understand how the energy or the energetics of the system or the thermodynamics of the system will affect the extent of chemical reactions that are occurring. To do that, we sort of have to go backward and review, this idea of enthalpy and enthalpy changes, where when we think of an enthalpy change, we can really think of the amount of heat that's being either transferred into the chemical reaction or being transferred out of the chemical reaction. And you know this because we've even talked about it during the equilibrium portions of this course, where we're talking about the idea of Le Chatelier's principle, where if you add heat to an exothermic reaction, you can actually drive the equilibrium back toward the reactants. In the reverse for an endothermic process. So just as a reminder, as a sort of reevaluation, the idea of the endothermic process being one where energy is required by the reactants to be able to produce the products. And the sign of the enthalpy change, or what we refer to as sort of like the heat change, is positive in that case. And when heat is transferred from the system, when it's a product, when it's produced along with the products, it's what we call an exothermic process. That's the sign of the enthalpy change for a situation like that would be negative. And I think that you all know that already, but I want to make sure that it's ultra super clear exactly what that means. And this is a little different type of presentation that I'm using today. I actually got up and just didn't feel like going into the college to record the videos for today, and so I just decided to do them here at home in this format, just to change things up a little bit. It gets hard whenever you're working from home and doing the same things day after day, so I'm like, let's do something a little bit different. Slightly different technology for me, just a different way of doing it, and I hope that change is good for you as well, because I know that we're all in the same boat of being at home and trying to stay at home, and that can be a challenge sometimes whenever you're in the same location when you're not used to that. Um, so just a little bit of a change up for today, for this week. So if we think about this reaction where we have sulfur dioxide reacting with hydrogen fluoride gas, to produce the products of sulfur tetrafluoride and water. The enthalpy change, and remember that little zero up there sort of tells us something about the state under which these are occurring, what temperatures and what pressures might exist for that to be true. We get 828 kilojoules per mole produced by, or consumed or used in that reaction. I hate to say consume because the energy doesn't really go away. It just gets transferred somewhere else. So consume maybe not the best word, but whenever we have an enthalpy change that's positive, that's endothermic, which means that heat is on the reactant side of the chemical equation. So essentially, this thermochemical equation is the same as what we have down here. Sulfur dioxide plus hydrogen fluoride to plus 828 kilojoules of heat will produce the products. And it's just the way that we think about that I want you to think about thermodynamics, and I want you to think about enthalpy changes, and soon to be entropy changes, and soon to be free energy changes, because that's where we're headed. So what does this look like graphically? Well, it looks something like this. If you would plot the enthalpy, all right, on the y-axis and the process or the progress of that reaction on the x-axis, what it's meaning is that when we start, the sulfur dioxide and the hydrogen fluoride gas are at a lower energy than the sulfur tetrafluoride and the 2 water. The difference in energy between the reactants and the products is equal to the enthalpy change for that particular reaction. So we have to push those reactants up the hill, up the energy hill to get those products. And the amount of pushing that we have to do is the difference in energy between the products and the reactants, which is the enthalpy change. It just gives us a way to visualize what enthalpy means. And I want to make sure that we understand that clearly before we move into or add some other pieces on top. So if we think about this in terms of an exothermic reaction, where we have sulfur plus oxygen, so the oxidation of solid sulfur or gaseous sulfur to produce sulfur dioxide, the enthalpy change for that reaction is minus 297 kilojoules per mole, which means it's exothermic, which we could write if we wanted to. It's completely non-formal, and I don't see anyone that really writes it like this, but to me it makes complete sense to write it as a chemical reaction with the heat in the chemical reaction. So sulfur plus oxygen to produce sulfur dioxide plus 297 kilojoules of heat. To me, that makes complete sense to think of it that way. And even if you're thinking about it in terms of how an equilibrium would shift, thinking about that heat as either a reactant or a product helps us to determine which way the equilibrium will shift. And so I think that this even helps us looking back on the Le Chatelier's principle stuff that we have done. Now, what does that look like graphically? So if we go back to our same or our similar plot of enthalpy versus progress of reaction, now we're starting off with 2 reactants that are at a higher energy than the sulfur dioxide. In theory, it shouldn't take much pushing to get those reactants to react to produce that product, because the product's at a lower energy, and we know that things in nature want to get to this state of lower energy. Now, the difference in energy between those 2 states, between the reactants and the products, is equal to the enthalpy change, minus 297 kilojoules. And so if we push those reagents a little bit, get them reacting to produce the product, the amount of energy that will be produced in that reaction or be given off from that reaction is the difference in energy between those 2 states. Now, like I said, and I'm sort of telegraphing a little bit, but you might think that when the products are at a lower energy than the reactants, that the reaction will always occur. And that's not always the case. And that's what we're going to spend most of the rest of our time talking about thermodynamics, trying to comprehend, is that it's not just the energy difference between the products and the reactants that matter. There are other factors that come into play, and we have to consider those whenever we're trying to think about whether a reaction will occur thermodynamically. And in fact, we're going to find that there's going to be one big energy term that we're going to call free energy, sort of like the ability of a system to do work. That we're going to combine all of our other energy terms, including enthalpy, into, so that we can then use the free energy to predict whether a reaction will occur. And I'm going to tell you that even when we get to that place, we might predict a reaction will occur, but it may not react. And we're going to look at some examples. Us sort of standing around in an oxygen environment is a great example of that. We should be burning up because thermodynamically, the oxygen wants to react with all of the organic molecules in our body, but it doesn't. And so why doesn't it? And we'll talk about that. So that's sort of our intro to thermodynamics. We're going to get into something more complicated in the next video, but that just sort of gives us a good footing to start our discussion on.